Hello, everyone. My name is Ryan Johnson, and I collaborated with some colleagues from CryptoWire for this research, Mohammed El Sabag and Angelo Stavro. And the title of our talk is Unprotected Broadcasts in Android 9 and 10. So here's the agenda for the talk. I'm first going to talk about intents and then protected broadcasts. Next, I'm going to talk about the unprotected broadcast vulnerability that's in Android open source project code, then some notable instances of the vulnerability. Next, I'll move to the resolution to fix the vulnerability, the disclosure process, and finally with some conclusions. So CryptoWire was jump-started by a DARPA project in late 2011, and some of our R&D has been supported by DHS, S&T, as well as NIST. And at CryptoWire, we focus on enterprise mobile security, providing software assurance, developer integration, mobile device management, threat feed, and security analytics. So Android applications are built using app components, and these are kind of independent code units which perform dedicated tasks. And over on the right are the 4 types of application components that Android provides from which a developer can build an app. So an activity, this app component is the only one that actually has a GUI, and it's like a GUI component that the end user actually directly interacts with. A service executes in the background, performing long-running tasks. A content provider provides access to structured data, and a broadcast receiver, which we're going to focus on today, can be thought of as an event listener, and a broadcast receiver will register for one or more events, and once they occur, the broadcast receiver is alerted. So all valid applications in Android have a manifest file. It's called an Android manifest.xml file. So this contains certain version information, such as the package name, the version code, the version name as well. And it also contains various settings and configuration data. An application will have to declare the application components it has in the manifest file. So at the bottom is an example of a broadcast receiver that's declared in the manifest file that registers for an action that is boot completed. So an intent is an IPC message. So this can be sent from one application component to another application component within the same app, or from one app to another app, or from one app to multiple apps. And intents can be classified into either explicit intents or implicit intents. And an explicit intent is one where the sender defines the exact receiver that should receive the intent. So at the bottom is an explicit intent where the sender says, I want to send this to the NFC application, and specifically the NFC boot completed receiver should receive this intent. And there's also implicit intents, which don't define a concrete receiver, but instead rely on an action string. And this provides loose coupling, where this intent can be sent, and also the receivers, there can be multiple receivers that register for this broadcast intent. So protected broadcast, this is a primitive in Android, which will allow certain system components to prevent third-party applications from sending broadcast intents with specific actions. So this is commonly used by the Android framework, also by system applications. And we can see 3 different protected broadcasts listed. There's connectivity change, boot completed, and locale changed. These are declared by the Android framework as protected broadcast, and this is to prevent third-party applications from sending them. It should be reserved for the system. So receiving a protected broadcast, this can generally be done by any process on the device. although the sender may also impose that the receiver has a specific permission in order to receive it. So this is the case with boot completed. You will need the boot completed permission to receive that specific intent. So going into detail on who can actually send protected broadcasts, over on the left is an Android 9 AOSP source code snippet from Activity Manager service. And this code is invoked when an application tries to send a broadcast intent. So first, it's going to check the UID of the sending app to see if it's any of the known system UIDs. If it's not, then it's going to check to see if the calling app, the app that's trying to send the broadcast, is persistent. And this is essentially done by setting the Android persistent attribute to true in the app's manifest file, although only system apps can actually be persistent or have that recognized by the system. And if neither of those cases are true, isCallerSystem is going to be false. So then when sending the broadcast intent, it's going to check to see if the action is a protected broadcast action. And if so, it's going to throw a security exception in the context of the caller. And this will occur when a third-party application tries to send a protected broadcast. So an APK file is essentially just a standalone Android application file. This contains the code and the resources. And here we see an ADB command, which lists the installed packages or APK files on the device. Here it shows the path to the APK as well as the package name. And you can see that looking at the path, the first app that's listed is in system priv app directory, and the next is in system app, and after that is vendor app directory. So the priv app directory is a special directory where apps contained in it are considered to be privileged. And one of the differences are that privileged applications can be whitelisted permissions through XML files on the system to grant them permissions which they won't actually need to ask the user to grant them. Another difference between app and priv app is which directories can actually register protected broadcasts or have them declared in their manifest file and have them be recognized by the system. So here we have a table from Android 8 to 11 and showing the directories where the applications contained in those directories can successfully register protected broadcasts and those that cannot. So looking at Android 8, it's all the directories, including the system framework and system app, priv app, can all register protected broadcasts. The only one that cannot is data app, and this is for third-party applications, and this is pretty much constant through all versions of Android. And there's a change made from Android 8 to Android 9 where the system framework as well as priv app directories can register protected broadcasts, but then app directories of those same partitions cannot register protected broadcasts, system app, vendor app. And the same is true for Android 10, although there are more exclusions for the overlay directories and some additional partitions. And for Android 11, after we reported this vulnerability to Google, they essentially made it so that any system app or pre-installed app can declare and protected broadcasts and have those be registered by the system, and then only third-party applications cannot. So how does the device know which applications are pre-installed? This is the responsibility of Package Manager service in the Android framework. So this is a backend service that provides information about installed apps. So a third-party application can access it, using the Package Manager class, which goes through the iPackage Manager interface, which will then invoke a method on Package Manager service in the Android framework. So Package Manager service scans partitions on system startup, and it looks in directories for applications. It parses their manifests to determine the installed applications, and the various configurations, as well as the broadcasts that they declare as protected. So here we're going to look at Package Manager Service, AOSP code for Android 10. Here is where the code where it will, scan the system priv app directory, and this directory, the apps that in this directory are going to be scanned with the scan as system flag, as well as the scan as privileged flag. Then moving to system app, where it will scan this directory with the scan as system flag. And as you can see, it is missing the scan as privilege flag. And any applications that are scanned and do not have the scan as privilege flag will have their protected broadcast drop. So you can see here, priv app is scanned with the scan as privilege flag, so it's going to maintain its protected broadcast. But applications in system app are not scanned with the scan as privilege flag, so its protected broadcast will essentially be dropped, and they are offered no protection at runtime. So kind of to summarize it, the system applications that are not present in a priv app directory in Android 9 or 10 will have their any protected broadcast that they declare in their manifest file. They will not be recognized by the system, which will then allow third-party or any applications, including third-party applications, to send them at runtime. So here we have the CVE ID as well as the CVSS base score of 7.3. So here's an example kind of how the vulnerability would manifest. So there is clutch.apk, and it declares a protected broadcast in its app manifest. System server at startup will parse the protected broadcasts in all the applications on the system, but any application that is not in a priv app directory will not have its protected broadcasts actually recognized by the system. So a third-party application can send a protected broadcast, and their protected broadcast won't be offered any protection at runtime. So it's able to send broadcast intents with these actions that apps not in a priv app directory declared as protected, but aren't protected at runtime. And this can result in privilege escalation because it can result in the third-party application sending spoofed messages that appear to be from the system but are not. So the receiving system application may trust that it's from an authorized user when it's really from the third-party application. So here is a command for a third-party application to send a broadcast intent. So here is that same action being declared as a protected broadcast. And if it's declared in an app that's in a priv app directory, when the third-party app tries to send it, it's going to be denied since it is recognized by the system. But if that protected broadcast is declared in an app that's in the app directory, then the system is not going to recognize it if it's Android 9 or 10, and the third-party application will be able to send that broadcast intent successfully. So the attack surface are app components that are accessible, they're exported, they're not permission protected, and they register for broadcast actions, which are not going to be protected at runtime, which is dependent on the declaring app's file system location. So the attack vector is sending broadcast intents with action strings, which apps have declared as protected, but actually aren't protected at runtime. So the requirements are a local app on the device that can actually broadcast intents, and the goal is privilege escalation. Due to sending these spoof broadcast intents, they appear to be from the system. Since it is a protected broadcast, but it's not being protected at runtime, but the source is really from a third-party application. So when we reported this to Google, in May of 2020, the affected major Android versions were Android 9, Android 10, and it was in Android Developer Preview 3, but we informed them So it wasn't actually ever in, Android 11 release. And they also backported the fix to Android 9 and Android 10. So we wanted to check to see if any Google devices were also affected. So we looked at the Google Pixel 4, and this contains 3 applications that have unprotected broadcast or declare, protected broadcasts. And based on the declaring app's file system location, they aren't actually protected at runtime. So we provide the build fingerprint and also the package names and their paths on the device. So one of the applications is called presence polling, and this application facilitates rich communication services, or RCS. You can see the path is system app, and this application executes with the phone shared user ID. And this application is hosted on googlesource.com as an IMS IP multimedia subsystem external project, and is present on the Google Pixel 3 and Google Pixel 4 devices. So this application declares some broadcast intents or broadcast actions as protected, which are not protected. So a third-party application can send these broadcast intents, and one of them will cause file corruption on an internal database, because this database mirrors, the official contacts provider. And when a third-party application sends a broadcast intent, it will essentially copy all the user's contacts into the database, independent of whether they're there or not, this increasing the size. And this can be repeated over and over arbitrarily to increase the size of the database in an app that's running as the phone UID. Also, there is the perfdump app, which was present on various vendors and models. And this application will profile processes using the Linux perf tools. You can see the app path is system app, and this application executes with the system shared user ID, which makes it, very powerful, since it's, considered, to be part of the system, and is granted a lot of permissions by default. So we've listed some of the vulnerable versions, which we've encountered. And the vulnerability is a command injection vulnerability due to a protected broadcast, which isn't protected at runtime, which allows a zero permission third-party application to, execute arbitrary commands, in the context of this app, which is the system user, which, you can have a lot of capabilities to, surveil the user if desired, record the screen, also programmatically change the keyboard with one that has key logging functionalities. So here are some snippets from the app's manifest file. It declares multiple protected broadcasts, and there's also a broadcast receiver which registers for some of these protected broadcasts. So here we've provided the CVE ID as well as the CVSS base score of 7.8. And the vulnerability is, a third-party application can, send a broadcast intent, embed a command to be executed, and send it to this application using a broadcast action it declared as protected, but is not protected at runtime due to its file system location, and have it execute the command in a non-interactive shell. So we informed Qualcomm of this vulnerability. They ranked it as high severity and listed the affected chipsets. So here's a small sample of some of the devices, which, contained the perfdump application, as well as, the version code and version name. There's also the QMMI app, and this is another pre-installed application that we found in various vendor devices and models. And the app path is system app, And it also executes with a shared system UID. So we've provided some version code and version name of the application, which we've encountered. And the vulnerability is it allows a zero permission third-party application to programmatically obtain the device IMEI, a second IMEI if the device has one, the Wi-Fi MAC address, the Bluetooth address, and the device serial number. And this is relevant certainly because in Android 10 that Google made it so that third-party applications cannot directly obtain non-resettable device IDs directly, although here they're being obtained indirectly through a vulnerable system app. So here's just a quick walkthrough for the vulnerability. We have the malicious app on the right and the QMMI app on the left. The QMMI app is in an app directory on Android 9 or 10 device. It declares a protected broadcast. The malicious app registers for the update message broadcast intent. It starts the main activity of the QMMI app. The QMMI app, according to its logic, registers for the broadcast action it declared is protected. The malicious app can send this since it's not actually protected at runtime. And then the QMMI app sends an implicit broadcast intent, which is received by the malicious app. It also can be received by any application that registers for it on the device. And then that broadcast intent contains a PII. And then optionally, the malicious application can start the default launcher and push a QMMI app into the background. So here's the fix. Here's the actual commit. And this is done to the package manager service. And on the right, as we saw previously, if an app was not scanned as scan as privileged, it would then drop the protected broadcast the app declares. So that code was removed. And on the left, if the application is not scanned as scan as system, then it will drop the protected broadcast that the app declares. But as we've seen previously, apps in the priv app are scanned as scan as privileged, and scan as system, and apps in an app directory are scan as system. So they will maintain their protected broadcasts, and only third-party applications will have them removed. And this fix was backported to devices that were vulnerable devices that are still supported for receiving an update. So here is the timeline. So back May 8th was the initial disclosure to the Android security team and affected vendors. Then on June 8th, registered the vulnerability through Google's issue tracker. The next day they acknowledged the submission. And then on the 15th of June, they, committed the fix. You can see the hash there. And on the 18th of June, they finished their initial assessment and ranked the vulnerability severity as high. And then in August 21st, they assigned the CVE. And in September 8th, they, changed the status of the vulnerability to fix and provided a bug bounty. And to conclude, it's would be certainly more secure to use some defense in depth design principles to employ multiple forms of access control when guarding components that are solely relying on protected broadcasts. Maybe you can also require that the sender have a signature level permission, and also providing some runtime feedback to developers, say if they're trying to register a protected broadcast and doesn't actually register, to help identify these cases in the future. And also when making significant changes to the system, ensuring that there is good communication. And here is our contact info, and thank you very much for attending our talk.